Hello, everyone, and thanks for joining us today. I'm Chloe Theobald from Charged, and it's a pleasure to have you with me and the Siemens team here. Our webinar today is a multi-physics approach to battery thermal management and runaway analysis, and it's brought to you by Siemens Digital Industry Software.
We finalized the design for passive thermal runaway protection. We can continue with the configuration of the thermal management system during the fast charge operation. The bus shall be charged with the so-called constant current, constant voltage profile. During this procedure, the battery gets charged with the constant current until the final voltage limit is reached. In the next step, the battery gets charged with that constant voltage while the current decreases. In our case, we have to charge the bus in a range between 20% and 99% SOC. Then additional criteria, we want to charge the cell with a minimal internal resistance to keep the generated heat of the cells during the charging as low as possible. The plot that you see here on the left shows the internal resistance value over the cell temperature. This plot is not the real internal resistance plot for this specific cell. It's from a different battery cell that I found on the internet, but it is used here just for demonstration purposes. Based on this plot, the optimal cell temperature during charging would be between a temperature between a range of 20 and 30 degrees. In this area, we would have a minimal internal resistance, and that would mean the cooling system would operate in the most efficient manner. To set up electric circuits inside StarCSim Plus, you can use the circuit editor tool. In this case, the circuit consists of 8 modules in a serial connection and is combined with 2 parallel branches. Branch 1 models the constant current phase of the charging procedure. It consists of a combination of a scalar circuit element and a resistance. The resistance in this setup, or the resistances in this setup, act like switches that can activate or deactivate a parallel branch. The scalar circuit element in branch 1 sets the current to 141 amps. The resistance that is used for the current control is 0 if the voltage is below the end voltage, and it jumps up to infinite if the end voltage is reached. This would block branch 1 and it would open branch 2. In branch 2, a voltage element continues a constant voltage charge until the SOC of the cell has reached a value of 99%. The resistance for the voltage control is infinite if the battery voltage is below the end voltage, and it jumps to 0 if it is equal or above the end voltage. To identify the required cooling system parameters, 6 simulations are performed with StarCSim Plus. The first 3 simulations keep the inlet mass flow rate constant and vary the fluid inlet temperature. The other 3 simulations keep the inlet temperature constant and vary the mass flow rate at the inlets. All 6 simulations can be run in parallel if you use a power on demand license from StarCSim Plus. In 3.9 hours, all simulations are finished, and it turns out that the simulation number 3 delivers the best results that will be shown on the following slides. On the plot on the right, on the plot on the left, you see the constant current and the constant, you see the constant current phase here with 141 amps, and you see where the circuit switches from constant current to constant voltage phase. This is the area where the current is decreasing in a nonlinear manner and where the constant is kept constant. Inside this plot, you see the voltage of the first module inside the battery. And as already said, we charge here between a range of 20% and 90% state of charge. On the left, you see the temperatures of the cell stacks that stay in a range between 27 and 24.4 degrees Celsius, what ensures an optimal low internal resistance, as you can see on the plot on the right. StarCSIM Plus enables you to visualize the 3D temperature distribution inside the battery pack, which allows you to identify hot and cold spots inside the battery. This information is useful to find ideal spots, for example, for thermocouple temperature sensors that you could place inside test batteries. Another important information is the temperature gradient over one cell, which is an information that you would, for example, need for aging simulations. So let's sum up what we achieved with the 3D simulations. We ensured a sufficient passive thermal runaway protection by identifying the required heat shield thickness. We scaled the complete battery, that is parametric, up to the heat shield thickness of 6 millimeters. And in the next step, we simulated a fast charging procedure, and we determined all of the required cooling system parameters for an efficient fast charging procedure and identified the optimal parameters. And in the last step, the 6 simulations that we used for different inlet boundary conditions can now be used to train a neural network model. Neural network models are the keyword for my colleague Sana, who will show you now how this reduced order models work and what benefit they bring in the design process of a battery. My presentation ends here, and I will hand over to Sana again. Thank you all for your attention, and I will see you later in the Q&A session. Thank you.
Thank you, Niels. I'm going to share my screen again. Okay, so in this part, let's continue with the battery thermal runaway simulation. And here's the question I would like to raise. What if the operating conditions are different during battery thermal runaway? I mean, like cells with a different initial state of charge or a different state of health. The runaway reaction rates could be different, and same thing regarding the heat and the gas released. Of course, we can answer this question by making arc tests under different conditions, but this solution is costly, which on top of that, it will extend the design cycle duration. So how about making virtual tests under different scenarios? This is possible with the SimCenter integrated workflow, since it offers predefined thermochemical reactions. It describes the physics-based phenomena which occurs during thermal runaway. Now let's have a deeper look on these phenomena. The 5 reactions here are exothermal reactions. This is a multi-physics model where each reaction rate depends on the operating conditions, such as the temperature or the reactants amount, like the fraction of lithium inside the solid electrolyte interface. Therefore, by predicting the heat released by each reaction, you can accurately predict the temperature rise inside the cell. In the same vein, this model predicts each reaction rate. As a result, you can predict the gas released by each reaction, depending on the dynamic operating conditions. I previously mentioned the thermal runaway dependency on the temperature and the reactants amount. But this is not the only operating conditions considered here. Indeed, the model accounts for the initial state of charge, which has a strong impact on the 2 reaction rates over here. On top of that, the state of health of the cell is considered as well to predict thermal runaway. This is because the reaction here accounts for the solid electrolyte interface. This solid electrolyte interface is a passive layer created between the electrolyte and the anode, and it causes cell aging. Consequently, it affects the state of health of the cell. Now you may raise the following question, and I think that I've seen this question in the Q&A. How to identify these physics-based model parameters? To address this specific task, first you can start with predefined parameters, which are available in SimCenter AimSim. This database includes the popular chemistries listed here in this slide. Of course, this database has been validated, and I put here at the bottom the references. Second, you can leverage the measurement data by testing the cell of interest, then use these data as a reference to adjust the model parameters. Finally, this solution offers a methodology guidance to fit the model parameters. Now, once the parameters are identified and the thermal runaway model is validated, you can run virtual tests under different operating conditions. This includes different initial state of charge and different state of health for the battery. From these virtual test results, you can integrate the heat release from reactions as well as the venting gas data into STAR CCM plots. In this step, you take advantage from the 3D multiphysics modeling approach as Niels presented previously. This integrated workflow to address thermal runaway analysis allows for modeling the complexity of these highly dynamic and multiphysics phenomena. You can explore the possibilities by virtually testing the different scenarios. The added value here is to ensure the decision confidence at an early stage of the design cycle to meet the battery safety requirements. Okay, once the battery pack design optimization is done, let's move to the following step of the workflow. At this stage, we need to move forward with system level and control design activities to ensure the battery performance and lifetime. In the following, I will present the battery pack model reduction workflow. We start from a 3D multiphysics model, then we leverage system simulation and artificial intelligence capabilities. Let's start with the biggest challenge here: how to keep 3D multiphysics details of a battery pack while ensuring real-time capability for system-level and control design activities. Indeed, the 3D geometry consideration is a key to predict the hotspots and the temperature gradients. On the other hand, with this approach, the computation time is not suitable to run live tests, including the vehicle subsystems and controls, or to enable thermal design and software in the loop and hardware in the loop. So how about the workflow which SimCenter offers to keep the balancing between the two approaches? The first step is to define which 3D multiphysics details we want to keep while ensuring real-time capability. Of course, we can customize these steps depending on the situation. In this example, we want to keep predicting the following results. The first one is the battery pack maximum temperature. We need to control the maximum temperature to ensure the battery safety and performance. In such a way, we detect the situations where the heat exchange is not sufficient to evacuate the heat flow from the cells. This also helps to limit the cell's degradation. The second result we want to keep here is the battery pack minimum temperature. This is to control the battery temperature gradient. So it's important to design the battery to minimize the temperature gradient because it can limit the performance and the lifetime of the cells. Also, at low temperatures, we see slower diffusion and intercalation with the possibility of lithium plating. This is an issue since lithium plating removes lithium from the active cell, so it reduces the cell capacity. On top of that, lithium plating can cause electrical shocks. Moreover, we want to predict the battery pack average temperature, which will be used as an input for the battery pack system model, which is a lumped model. We also want to control the voltage and the state of charge and keep predicting the total heat flow rate released from the cells. Because when you integrate the system, this heat will be released in the coolant loop. So we want to ensure the system energy balance. Now, once the key results from 3D are determined, let's move to the workflow automation to generate a reduced battery pack model. The model architecture we offer here is the following. The battery pack minimum, maximum, and average temperatures are predicted using artificial intelligence approach, while the voltage, the state of charge, and the heat released are predicted using system equivalent circuit model. So this is a hybrid approach using both artificial intelligence and system equivalent circuit models. Let me start with the workflow to develop the artificial intelligence part of the reduced model. The 3 steps here to ensure an accurate machine learning model are the following. First, we need to determine the artificial intelligence model inputs and outputs. Second, we need data for the model training and validation purpose. And finally, we must choose the right reduced order model type, which suits best this specific application. Regarding the artificial intelligence model inputs and outputs, we already know the outputs from the previous step, which are the battery maximum, minimum, and average temperatures. From the other side, the inputs are the variables to which the outputs are sensitive. So the inputs are the following: the current, the coolant mass flow rate, the coolant temperature, as well as the voltage. The model training and validation data are generated from StarCCM+, as Niels mentioned previously. We run 6 fast charging simulations with different boundary conditions for the cooling system. Then, using the SimCenter ROM builder, we directly import the CSV files with a graphical user interface. Next, once the data is automatically imported, we follow this streamlined workflow using the SimCenter ROM builder. We first create a dynamic neural network model. Second, we take advantage of these model templates to get the right hyperparameters. And finally, we run the training and we check the training and validation fidelity. In this case, the training and the validation fidelity shows respectively 99% and 98%, allowing a very high accuracy. So that was the artificial intelligence part of this hybrid reduced order model. Now, regarding the system equivalent circuit model, which is a battery pack model in SimCenter AIMSIM, the workflow to develop this model is more than convenient. This is thanks to the common SimCenter battery electrothermal identification tool. This tool automatically identifies the battery electrothermal parameters for both SimCenter AIMSIM and SimCenter StarCCM+. So we just need to hit the button here to generate the same equivalent circuit parameters for both SimCenter tools. And I put on the slide here a link to a blog which explains and gives more details about this battery electrothermal identification tool. At this stage, we end up with a hybrid model which is fully integrated in SimCenter AIMSIM. At the left side here, we have the equivalent circuit model. So here, this part. So here we have the equivalent circuit model, which predicts the voltage, the state of charge, as well as the heat released. This model is connected to the artificial intelligence model here. The latter predicts the battery pack, maximum, minimum, and average temperatures. Regarding the model fidelity, here is an overview here of the validation error for all predicted results. And the average validation error is 99.2%. On the other hand, the computation time is 0.04 seconds for a 2,200-second fast charge simulation. So this hybrid model is real-time capable for software in the loop and hardware in the loop test, while preserving a very high accuracy. Now, to sum up, the main challenges addressed in this webinar are the battery safety, performance, and lifetime compliance. And this is with short design cycles and development cost reduction. To address these challenges, SimCenter offers an integrated workflow solution to model the complexity, such as thermal runaway analysis, which is a multi-physics and highly dynamic phenomena, or the battery pack model reduction, which is real-time capable while preserving high accuracy from 3D multi-physics simulation. And the added value here is to ensure decision confidence. With this solution, you can explore the possibilities while reducing testing costs, thanks to virtual testing and design exploration capabilities. From this, the solution enables insight while achieving speed and agility. Finally, the streamlined workflow allows to go faster and stay integrated. Consequently, it connects all your activities. Well, that's all from my side for this webinar. Thank you all. Hope that was insightful for you. And please let us know, Niels and myself, if you have any question.
Thank you for watching. To learn more about this topic, check out the links in the description. And if you enjoyed what you saw, like the video and subscribe to the channel.